Imagine this. It's 1990, Japan. You're living near Osaka. Your baby is asleep. The house is silent. Suddenly, boom, your windows rattle. Your baby screams. Was it an explosion? A fighter jet? No, it was a train. Japan's bullet train, the Shinkansen, was facing a $50 million crisis. Engineers had pushed speeds to 200 miles per hour, but they'd hit a wall of physics. Every time the train entered a tunnel, it created a massive pressure wave. When it burst out the other side, a thunderous tunnel boom heard up to a quarter-mile away. The public was furious. Lawsuits mounted. The railway engineers were desperate. They needed a breakthrough. Or maybe they just needed to go bird watching. Enter Eiji Nakatsu, General Manager of Technical Development for J.R. West Railway. But he had another passion. Nakatsu was a devoted birdwatcher, obsessed with the engineering elegance of nature. And he kept thinking about one particular predator that seemed to defy physics, the kingfisher. Look at this bird. It dives at high speed to catch fish underwater. Think about what's happening. Air offers little resistance. Water is 800 times denser. Hitting water at speed is like hitting a wall. A belly flop creates a massive splash and serious pain. The fish scatter immediately. The hunt fails. But the kingfisher? It enters the water with barely a ripple. No splash, no noise, no warning. The fish never see it coming. Nakatsu had revelation. If this bird can transition from low-density air to high-density water without creating a shock wave, could a train do the same entering a tunnel? The solution wasn't a more powerful engine. The solution was a better nose. A nose designed by 60 million years of evolution. Let's understand the physics. The old bullet trains had rounded noses. Aerodynamic right? Wrong. When that round nose hits dense tunnel air at high speed, it pushes air molecules forward. They bunch up, creating high pressure directly ahead. That pressure builds and builds. And when it escapes, boom. But the kingfisher's beak operates differently. It's not just sharp. It's what engineers call a rotational paraboloid, an elongated teardrop perfectly streamlined. Think of it like this. Old train nose is like your hand pushing through water flat. Kingfisher nose is like your hand slicing through water sideways. One creates a wave, the other disappears. When this shape enters air or water, it doesn't push the medium forward. It parts it smoothly to the sides. The beak creates a gentle gradient rather than a sudden shock. Molecules are guided around in smooth laminar flow. It's the difference between punching through a wall and sliding a key into a lock. But the nose wasn't the only problem. The pantograph, the mechanical arm connecting to overhead wires, was creating deafening noise at high speeds. Wind screaming over metal at 186 miles per hour. So Nakatsu looked to another master of silence, the owl. Owls are the silent hunters of the night. They swoop within inches of prey without making a sound. How? Owl wing feathers have serrated edges, like the teeth of a comb. These serrations break up large turbulent vortices into tiny, quiet microturbulences. They transform roar into whisper. Nakatsu borrowed that design too. He carved serrations into the pantograph structure. And for the base, he studied the Adelia penguin, whose streamlined belly minimizes drag rocketing through water. He applied those curves where the pantograph met the train body. Now Nakatsu had his blueprint, not from textbooks, from the natural world. Imagine walking into a boardroom of Japanese railway executives in the early 90s and saying, "Gentlemen, I propose we redesign our iconic train to look like a bird's beak." Many were skeptical. The proposed nose was 50 feet long. It looked strange, almost comical. Fewer seats in the front car, a manufacturing nightmare, and expensive, very expensive. But Nakatsu insisted on testing. Visual wind tunnel testing. His team spent years in wind tunnels and supercomputer simulations, thousands of tests, scale models carved from wood and clay precisely matching the Kingfisher's beak proportions. The results appeared. The engineers fell silent. The old design showed angry red zones, high-pressure slamming walls, exploding outward. But the Kingfisher design? Smooth blue gradient flows. The pressure wave had been tamed. The numbers didn't lie. This beak design performed better than anything they'd engineered in 50 years. The owl-inspired pantograph tests were equally impressive. Noise levels dropped dramatically. They had their proof. Now they had to build it. The 500 Series Shinkansen. A machine made of metal and electronics. Yes, but designed by evolution. March 1997. The 500 series launched. The world was watching. The train accelerated. 100, 150, 186 miles per hour, approaching the tunnel at full speed. It plunged into darkness. Silence. The tunnel boom was gone. Residents reported they could barely hear the train anymore. Lawsuits stopped. Complaints ceased. But here's the remarkable part. The biomimicry design didn't just solve the noise problem, because the train cut through air with such fluid efficiency, aerodynamic drag was reduced by 30%. The train could maintain higher speeds with less effort. The 500 series became the fastest Shinkansen ever built, 186 miles per hour in regular commercial operation. And energy consumption? Down 15%. Let that sink in. 15% energy savings on a national rail network. Millions of dollars saved every year. Thousands of tons of CO2 emissions avoided annually. All because one engineer stopped staring at blueprints and started watching birds. We humans can be arrogant. We consider ourselves the greatest inventors. We're proud of our 200 years of industrial revolution, smartphones, rockets, artificial intelligence. But here's a humbling truth. Humans have been around for 200,000 years. Life on Earth has existed for 3.8 billion years. During that immense span, nature has conducted trillions upon trillions of experiments. Every species alive today represents a solution that won the most brutal competition imaginable. The struggle for survival across millions of generations. The kingfisher's beak isn't random. It's the result of 60 million years of evolutionary refinement, tested in real-world conditions, optimized through countless iterations. If a design failed, that lineage went extinct. If it succeeded, it was passed down, refined, optimized. Every problem we're trying to solve right now, energy efficiency, aerodynamics, material strength, water, filtration, structural engineering, has already been solved. The patents exist in the forest, in the ocean. We just need to learn how to read them. And here's the beautiful irony. The more we learn from nature, the more we realize we need to protect it. Every species that goes extinct is like burning a library book we haven't read yet. That kingfisher that saved the bullet train, its habitat is threatened by urbanization. The biomimicry revolution is teaching us something profound. Conservation isn't just about saving animals. It's about saving our own future innovations. Because every creature out there holds a solution we haven't discovered yet. In 2026, we face climate challenges. Every engineer is asking, how do we build sustainably? Nature already knows. 3.8 billion years of R&D, zero waste, zero pollution, perfect efficiency. The kingfisher doesn't need lithium batteries. It doesn't generate carbon emissions. It simply works. And we're finally smart enough to copy it. If this fascinates you, there's an entire field waiting. Biomimicry engineers are in high demand. Architectural firms hire them. Tech companies recruit them. Sustainability consultants need them. The future doesn't belong to those who fight nature. It belongs to those who learn from it. The kingfisher didn't ask for royalties. The owl didn't demand recognition. But they taught us something more valuable than any technology. We don't need to conquer nature. We need to learn from it. This field is called biomimicry, and it's not just about trains. Velcro, inspired by burrs sticking to dog fur. Sharkskin patterns reduce drag on aircraft. Spider silk studied for bulletproof materials. Termite mounds inspire sustainable building ventilation. The future of technology isn't purely artificial. It's biological. Visual, next episode teaser, mosquito needle close-up. Next episode, How a mosquito's mouth inspired the world's most painless medical needle. Nature's patent number 2. So the next time you see a bird or a bug or a leaf, look closer. You might be looking at the blueprint for the next billion-dollar invention. Because remember, nature invented it first. I'm Carl. This is Nature's Patent. If you found this story fascinating, hit that subscribe button and let's decode the next blueprint together. The library of nature is vast, and we've only just begun to read it. Drop a comment. What innovation from nature should I cover next? I read every single one.